Welcome to the Explainer. Today, we're taking a wild journey from the surface of the Earth straight down into deep, subterranean rock. The engineering required to extract oil and gas is mind-bogglingly complex, but by breaking it down step by step, we're going to see exactly how this modern marvel is achieved, taking it all the way from a patch of empty dirt to a fully producing energy asset.
Okay, let's dive into this. Here is our structural roadmap. We'll be tracking the literal life cycle of a well across 5 stages. 1. Setting up the rig. 2. Drilling deep and sideways. 3. Securing the wellbore. 4. Connecting to the reservoir. And finally, 5. Controlling the flow.
Section 1. Setting up the rig. Before we even think about touching the dirt, we've got to build out the massive surface equipment. Let's do a rapid-fire breakdown of a rotary drilling rig. You've got the derrick or mast. That's the classic towering framework you instantly picture. Then there's the drawworks, which is essentially a giant heavy-duty hoisting machine. Above that, the crown block and traveling block pair up as a massive pulley system to lift and lower absolutely insane weights. And to actually spin the drill string, you know, that long, heavy column of pipe reaching down into the ground, we rely on the swivel or top drive and the rotary table. Put it all together, and you've got the mechanical muscle that makes the physics of drilling possible.
And this brilliantly illustrates how we adapt when we aren't on dry land. For offshore drilling, we basically look at 2 main structures, jackups and semi-submersibles. For shallow water, up to about 400 feet deep, we use jackups. These rigs literally have movable legs that push down and rest right on the seafloor. On the flip side, deep water environments require a whole different beast, semi-submersibles. These are floating behemoths with submerged pontoons. Because the water is far too deep for legs, they rely on insanely advanced dynamic positioning systems to just float there, staying perfectly stable over the wellhole.
Now, before a bit ever touches the earth, we have to install the ultimate safety mechanism, blowout preventers, or BOPs. Picture these as massive, high-pressure safety valve assemblies placed right on top of the wellhead. They use a combo of sealing mechanisms, specifically annular and ram preventers. Why are they so crucial? Well, if there's an unexpected surge of high-pressure fluid from the rock, what drillers call a kick, these valves can slam shut in a matter of seconds. Boom! The well is completely sealed, preventing a catastrophic blowout. They are literally the front line of rig safety.
Section 2. Drilling deep and sideways.
Let's move to the actual physical descent into the earth and see how this builds. As the drill string turns and grinds into the rock, we pump down a highly specialized fluid called drilling mud, usually made of a clay called bentonite. This stuff pulls off 4 vital jobs at once. First, it cools and lubricates that rapidly spinning, incredibly hot drill bit. Second, it flushes the broken rock cuttings back up to the surface so the hole doesn't clog. Third, it exerts hydrostatic pressure, meaning the sheer heavy weight of this mud pushes outward to stop fluids in the surrounding rock from violently entering the well. And fourth, it plasters the walls, forming a mud cake that physically stabilizes the raw wellbore. It's effectively the lifeblood of the whole operation.
But that brings up a pretty fascinating engineering challenge. What if the target underground reservoir isn't situated directly straight down beneath our rig?
Well, in modern drilling, we rarely just dig straight down anymore. We use directional and horizontal drilling. By hooking up steerable mud motors and this crazy advanced tech called Rotary Steerable Systems, or RSS, engineers can literally bend the wellbore away from vertical. They steer the drill bit horizontally right through a specific rock layer for miles. This is an absolute game changer because it dramatically maximizes our contact area with the underground reservoir, letting us extract way more resource from a single surface location without needing a bunch of different rigs up top.
Section 3. Securing the wellbore.
Okay, we've reached our target depth, but if we just pulled our drill pipe out right now, the immense, crushing pressure of the earth would cause the hole to immediately cave in on itself. To prevent that, we install casing strings. These are sequential layers of heavy-duty steel pipe dropped into the wellbore. It starts with the widest conductor casing at the very top, then the surface casing, the intermediate casing, and finally the production casing running all the way down to the reservoir. These steel walls lock in the well's integrity, but most crucially of all, that surface casing is specifically designed and placed to totally seal off and protect our shallow freshwater aquifers from any contamination.
But hey, steel pipe just sitting in a dirt hole isn't enough. We have to do cementing. Think of this like caulking a window to stop a draft, but on a massive, subterranean scale. Cement is pumped all the way down the inside of the casing, and it forces its way back up the outside, completely filling up the annular space between the steel pipe and the raw rock wall. This secures the casing permanently in place and ensures that all those different underground zones are perfectly isolated from one another.
Section 4. Connecting to the reservoir. So the well is drilled, it's wrapped in steel, and securely cemented. But before we can start pumping any oil or gas, we have to actually coax the resource out of the rock. Since the well is sealed tight by that steel and cement jacket, we deliberately have to puncture it. Step 1, we lower specialized tools called perforating guns down into the production zone. Step 2, we blast explosive shape-charge holes straight through the steel casing and the cement. Step 3, this finally successfully connects the internal wellbore directly to the reservoir rock outside. It's a dramatic, explosive sequence for sure, but it's incredibly precise and highly controlled.
Now, what's really interesting about this process is how we tackle low permeability rock, like shale. Sometimes the oil or gas is tightly trapped in microscopic pores and just won't flow easily toward the perforations we just made. To solve this, we use hydraulic fracturing, commonly known as fracking. Fluid is injected straight down the well under ultra-high pressure. The sheer physical force of this fluid literally cracks the tight rock wide open, creating a massive network of artificial flow pathways deep underground.
So the crucial point is, what happens when we stop pumping and that extreme fluid pressure drops? Naturally, the immense weight of the earth wants to crush those newly induced fractures right back shut. That's exactly where proppants come in. Proppants are solid particles, think highly processed sand or tough ceramic beads, that are pumped in alongside the fracking fluid. When the pressure releases, these proppants act like millions of tiny microscopic doorstops holding the fractures wide open so the oil and gas can continuously flow into the well.
Section 5. Controlling the flow.
This is the ultimate transition, moving from the dynamic process of drilling and completing the well to successfully producing from it day after day. People often mix up these two vital pieces of equipment, so let's clearly delineate them. During the drilling phase, we use the wellhead. Its job is purely structural. It holds the immense hanging weight of all those steel casing strings we talked about, and it seals the borehole while the rig is active. However, after the well is fully completed, the massive drilling rig packs up and leaves, and we install the Christmas tree right on top of the wellhead. The Christmas tree is a permanent, complex system of valves, gauges, and chokes specifically built to safely control the flow of fluid coming out of the well.
When you step back, just consider the sheer scale of human ingenuity required to safely extract these resources from miles beneath our feet. We've gone from towering steel structures on the surface to navigating steerable bits through solid rock miles away, isolating zones with cement, and managing crushing pressures with explosive precision. It really makes you stop and wonder, what other invisible subterranean marvels power our everyday world? Think about that and keep exploring.